I have a classical example of lead optimization I want to show you. This is the Hiv1 protease. It's a key protein in the HIV virus that fulfills the same role as the protease in SARS roughly. So this is important for the virus to cut up its own proteins and infect the host cell. If we could kill the function of this protein, we would be able to combat the HIV virus. So in this case, they started to roughly design a pharmacophore, although here it's shown as a molecule. This is not the chemistry class, so forget about what I'm calling these molecules, but I need to describe roughly what it is. So this is a symmetric, a mirror image diol to alcohols, and it had some activity. Then we created a pharmacophore from that. Well, not me personally, but the field. Do you see here the schematic representation? Based on that pharmacophore, you found hits in databases. So this is a particular database hit, but it's too large and a few too many groups. It's certainly not ideal. Based on that database hit, people created a simpler design, and here you don't draw the entire side groups. So based on their knowledge of chemistry and the molecule and everything, we hope that this should fit the size of the cavity in the middle here better, and also have nice binding properties that should bind those red side chains in particular. In the next phase, you extend this to make it a diol again, and you add a bit of urea. I actually don't remember why they added urea. Obviously, they hoped that it would bind better. Then you optimize the stereochemistry for binding, and there are probably another 20 stages in between here that I don't show you. And in each iteration here, they would have to do additional tests and see, is this improving it or deteriorating it? And I bet they didn't show the stage that deteriorated it. There is a lot of trial and error here. Based on all these iterations, eventually they came up with this molecule that is somewhat reminiscent of the original molecule, but quite a bit different, right? This molecule is the Hiv1 protease inhibitor, and this was the first ever really computationally designed drug on the market. This has saved countless of lives because this is one of the early HIV break medicines. So we can't really treat HIV, right? But we can postpone the whole infection, make it slow down so much that you can basically live the rest of your life. The problem is that this virus is very good at mutating. So once you're starting adding this, you're going to create a selective pressure that if this molecule binds in the middle of the Hiv1 protease, the protease might start to change those red side chains or the purple ones there to make it more difficult for this molecule to bind. Again, purely by chance, of course, but viruses with that mutant will have an increased probability of surviving. So people have had to develop new Hiv1 protease inhibitors, improve the existing ones, and do the same thing for a ton of other molecules fighting HIV-1 too. The problem with HIV is that it's a very rapidly mutating virus. Thank God, SARS-CoV-2 appears to be a much slower virus, and it's much easier to, say, for instance, design a vaccine against the SARS virus.